Welcome! Today, we'll explore an interesting problem called Clumsy Factorial. This problem challenges us to compute a factorial using a specific sequence of operations: multiplication, division, addition, and subtraction. We'll break it down step by step and cover the most efficient way to solve it. Let's dive in. The problem we are tackling is called the Clumsy Factorial. Normally, the factorial of a positive integer n is the product of all positive integers from n down to 1. However, in this problem, we are asked to evaluate the factorial in a clumsy way by following a fixed sequence of operations: multiplication, division, addition, and subtraction. These operations are applied cyclically in that specific order. First, we multiply the current number by the next one, then divide the result by the following number, add the next, and subtract the one after that. This process is repeated until all numbers from n down to 1 are exhausted. The input to this problem is a single integer n, with the constraint that n is between 1 and 10,000. The output should be an integer representing the result of this clumsy factorial calculation. Let's look at an example to better understand the process. Suppose the input n is 4. We start with the numbers 4, 3, 2, and 1. First, we multiply 4 by 3, which gives us 12. Then, we divide 12 by 2, resulting in 6. Next, we add 1 to 6, arriving at a final result of 7. Therefore, the output for n equal to 4 is 7. Now, consider another example where n is 10. This will involve more numbers and multiple groups of operations. For n equal to 10, we begin with the numbers from 10 down to 1. The first group involves the numbers 10, 9, 8, and 7. We multiply 10 by 9 to get 90, then divide 90 by 8, which results in 11 after integer division. Adding 7 gives us 18. In the second group, we handle the numbers 6, 5, 4, and 3. Multiplying 6 by 5 yields 30, dividing 30 by 4 gives 7, and adding 3 results in 10. Finally, the last group only includes the numbers 2 and 1. Here, we simply multiply 2 by 1 to get 2, as there are no more operations to perform. To combine these results, we sequentially subtract 10 from 18 and then add 2, which gives us a final output of 12. This shows how the clumsy factorial operates across multiple groups of numbers. For the last example, when n is equal to 1, the calculation is straightforward. Since there is only one number, there are no operations to perform, and the result is simply 1. The problem also specifies some constraints to keep in mind while solving it. The value of n will always be between 1 and 10,000, and all intermediate calculations will fit within a 32-bit signed integer. Additionally, division in this context is performed using integer division, meaning any remainder is discarded, and the result is truncated towards 0. This behavior is crucial to achieving the correct output. When handling edge cases, there are a few important scenarios to consider. For very small inputs, such as n equal to 1, 2, or 3, the operations are limited by the number of available integers. For example, with n equal to 2, we simply calculate 2 multiplied by 1, resulting in 2. With n equal to 3, we compute 3 multiplied by 2, then divide by 1, giving a result of 6. For very large inputs, like n equal to 10,000, the algorithm must be efficient to avoid exceeding time or memory limits. Finally, when there are fewer than 4 numbers remaining in the sequence, we only apply the operations that are available in order, ensuring the calculation is completed correctly. To solve the clumsy factorial problem, the task involves calculating the factorial of a number, n, but with a twist. Instead of the traditional multiplication of all numbers, we follow a specific sequence of operations: multiply, divide, add, and subtract. These operations are applied repeatedly in this order, starting from n and working down to 1. One straightforward way to approach this is by directly simulating the process as described in the problem statement. This brute force method involves maintaining a running result, which is initially set to n, and iterating through each descending number while applying the operations in a cyclical manner. To manage this, we track the current operation using the modulo operator with 4, as the operations repeat every 4 steps. This approach is easy to implement and mirrors the problem's requirements closely, making it a natural starting point for understanding the solution. However, the brute force approach has its drawbacks. While its time complexity is technically O(n), the repeated multiplication and division operations can be computationally expensive, especially for larger values of n. Additionally, this method doesn't take advantage of any patterns or shortcuts in the sequence, which means it may not handle edge cases or larger inputs efficiently. By exploring the problem further, we can observe certain patterns that simplify the calculations. One key insight is that the sequence of operations multiply, divide, add, and subtract follows a predictable cycle. For larger values of n, the result becomes stable, and the contributions of terms beyond the first few become more consistent. This means that the first few terms have the greatest impact on the result, while the later terms can often be handled using a generalized formula. Special cases, such as when n is small, less than or equal to 4, require additional consideration, but for larger values, grouping terms into chunks of 4 allows us to streamline the computation. To implement this optimized approach, we begin by explicitly calculating the result of the first group of terms, as it has the most variability and impact on the final answer. After processing the first group, the remaining terms are handled in chunks of 4, leveraging the predictable pattern of their contributions. This allows us to substitute repeated calculations with a formula derived from the cyclical nature of the operations. For example, subsequent groups can be evaluated as alternating additions and subtractions of predictable values. For small values of n, such as when n is less than or equal to 4, we introduce conditionals to handle these edge cases directly, ensuring correctness. This optimized method reduces unnecessary computations and simplifies the problem for larger values of n, while maintaining an O(n) time complexity. The trade-off is that this method is slightly more complex to implement, as it requires careful observation of patterns and precise handling of edge cases. The chosen strategy for solving the clumsy factorial problem is the optimized mathematical approach. This method stands out for its efficiency, as it leverages the repeating pattern of operations to reduce redundant calculations. By explicitly calculating the first group of terms and deriving a formula for the remaining groups, we streamline the computation and make the solution more scalable for larger values of n. Additionally, by incorporating conditionals for small values of n, we ensure that all edge cases are handled effectively. While the brute force approach is simpler and more intuitive, its inefficiency for larger inputs makes it less practical. On the other hand, the optimized method requires a deeper understanding of the problem but offers significant performance benefits. Overall, this strategy strikes a balance between correctness and efficiency, making it the most suitable choice for tackling the clumsy factorial problem. The clumsy factorial problem is an interesting twist on the traditional factorial operation. Instead of simply multiplying all integers from n down to 1, we introduce a fixed sequence of operations: multiply, divide, add, and subtract. This sequence is applied cyclically to the descending integers, starting from n. It's important to note that these operations are performed strictly from left to right, without regard to the usual precedence rules for arithmetic. For instance, if n is 6, the sequence of operations would look like 6*5/4 plus 3 to 2*1. Integer division is used here, meaning the result of any division is truncated towards 0 to ensure the output remains an integer. One key observation is that the first few operations, multiplication and division, tend to dominate the result due to their order and relative impact. Additionally, because the operations repeat every 4 steps, the problem naturally divides into manageable chunks of 4 numbers, which simplifies both understanding and implementation. To solve the problem, we start by breaking it into smaller steps. First, process the numbers in groups of 4 when possible, applying the operations in the specified order. For each group, calculate the result step by step, ensuring that you handle truncation for division. When the number of integers is not a multiple of 4, the leftover numbers at the end are handled directly, without completing the entire cycle. Small values of n, like 1 or 2, are special cases and should be dealt with separately since no full operation cycle can be performed. The implementation begins by initializing the result with the value of n and setting up a variable to track intermediate computations. We then use a loop to process the remaining numbers in descending order, cycling through the operations as we go. Multiplication and division affect the intermediate value directly, while addition and subtraction modify the cumulative result. Finally, any remaining intermediate value is added back into the result to complete the computation. When fewer than 4 numbers remain at the end of the sequence, the operations are applied directly to them. After processing all the numbers, the cumulative result will hold the value of the clumsy factorial. Recognizing the repetitive nature of the operation cycle is key here, as grouping the problem into chunks of 4 allows us to focus on smaller, predictable subproblems. Another critical insight is that the left-to-right order of operations is a departure from standard arithmetic rules, so we must take care not to apply precedence incorrectly. For small values of n, such as 1, 2, or 3, special handling is required since we don't have enough numbers to complete a full cycle of operations. Additionally, integer division truncates towards 0, so our implementation must account for this to ensure accuracy. Solving this problem doesn't require complex data structures, just a few basic variables to track the result, the current intermediate value, and the operation cycle. This simplicity keeps the solution both efficient and easy to implement. The lack of auxiliary data structures makes this approach highly memory efficient. With only a few variables, we achieve a constant space complexity of O(1). Meanwhile, the time complexity is O(n), because we process each number from n down to 1 exactly once. This ensures the solution is both fast and scalable. To implement the solution, we begin with base cases for small values of n. For instance, if n is 1, we simply return 1, and for n equals 2, the result is 2 * 1 equals 2. For larger values, we initialize the result to n and decrement n to start processing the next number. We also use a variable to track the current operation in the cycle. Multiplication and division are applied directly to the intermediate value, while addition updates the cumulative result, and subtraction either subtracts directly or prepares for the next cycle. The modular arithmetic of the operation counter ensures that the operations are applied cyclically, and any remaining numbers at the end are handled appropriately. In the final part of the implementation, addition and subtraction operations are completed by updating the result variable as needed. The intermediate value is reset after addition to prepare for the next number in the sequence. For subtraction, the value is directly subtracted from the result. The loop continues, decrementing n and cycling through the operations until all numbers are processed. At the very end, any remaining intermediate value is added back to the result to ensure the computation is complete. The final result is then returned. This implementation is both time efficient, as it processes every number only once, and space efficient, as it uses just a handful of variables. The careful handling of edge cases and the modular approach to operation cycling make the solution robust and easy to code. This straightforward algorithm demonstrates how a seemingly complex problem can be broken into smaller, repetitive components, making it manageable and efficient to solve. Here, we define a Python class called solution and implement the clumsy method inside it. This method calculates the clumsy factorial of a given number n. We start by initializing the result variable to 0, which will store our final output. Additionally, we use a flag called first_group, set to true initially, to help us handle the first group of operations separately. The main logic is implemented inside a while loop, which continues as long as n is greater than 0. Inside the loop, we first set the variable current to n and then decrement n by 1. At this stage, we begin processing groups of 4 operations: multiply, divide, add, and subtract. If there's still a number left, we multiply current by the next number and decrement n again. Similarly, if another number is available, we perform integer division on current and further decrement n. After handling multiplication and division, we check the first_group flag. If it's true, we add the current value to the result, marking the end of the first group, and set first_group to false to ensure subsequent groups are handled differently. For all remaining groups after the first one, we subtract the current value from the result instead of adding it. This ensures that the alternating pattern of addition and subtraction is maintained correctly. Finally, we check if there are any numbers left unprocessed. If n is still greater than 0, we simply add that number to the result and decrement n. This step accounts for any leftover numbers that don't fit into a complete group of 4 operations. Once the loop exits, meaning all numbers have been processed, we return the final result. This implementation efficiently handles the clumsy factorial calculation by systematically grouping operations and applying the appropriate arithmetic rules. The approach is both concise and adheres to the problem's requirements, ensuring correctness even for edge cases like small values of n. Here, we start with the Java implementation of the clumsy factorial problem. First, we define a class called solution and the method clumsy, which takes an integer n as input. The variable result is initialized to store the final output, and isFirstGroup is a Boolean flag used to handle the first group of operations differently, as the first group is always added to the result. The main logic is built around a while loop that continues as long as n is greater than 0. Within this loop, we process the numbers in groups of 4, starting with the current value of n. After decrementing n, we check if the next operation, multiplication, is possible. If so, the current value is multiplied by the next number, and n is decrement again. Similarly, if division is possible, the current value is divided by the next number, followed by another decrement of n. These steps ensure that the multiplication and division operations are performed in sequence. Finally, we check whether this is the first group of operations. If it is, the result is updated by adding the current value. If it's not the first group, we subtract the current value from the result instead. This distinction between addition and subtraction is crucial for maintaining the alternating pattern required by the problem. After handling multiplication, division, and addition or subtraction, there's one more step. If there's still a number left, we simply add it to the result, as any remaining number at this stage is part of the sequence that wasn't included in the earlier operations. With this structure, the loop processes all numbers in groups of 4, ensuring the correct order of operations is followed. Once the loop finishes, the result is returned as the final output. This implementation efficiently handles the clumsy factorial calculation by systematically applying the required operations in the correct order, while managing edge cases like leftover numbers and the first group's special handling. To solve the clumsy factorial problem for clumsy 4, we start by initializing the variables. N is set to 4, result is initialized to 0, and a flag first_group is set to true, indicating that we are processing the first group of operations. Now, we start with the first group. The current value is initialized to 4. First, we multiply current by 3 to get 12, then divide it by 2, resulting in 6. Since this is the first group and first_group is true, we add this current value to the result, making result equal to 6. Afterward, we add the remaining value of n, which is 1, to the result, giving us a final value of 7. Since n has now reached 0, we exit the loop and return the result, which is 7. The final output for clumsy 4 is 7. Now, let's analyze the process for clumsy 10. We start by initializing the variables. N is set to 10, result is 0, and first_group is again set to true. In the first group of operations, we begin with current equal to 10. Multiplying it by 9 gives 90, and dividing by 8 results in 11. Since this is the first group, we add this current value to the result, updating it to 11. Then, we add the remaining value of n, which is 7, to the result, making it 18. At this point, n is decrement to 6, and we move on to the next group of operations. In the second group of operations for clumsy 10, we start with current equal to 6. Multiplying it by 5 gives 30, and dividing by 4 results in 7. Since this is not the first group, we subtract this current value from the result, reducing it to 11. Next, we add the remaining value of n, which is 3, to the result, bringing it to 14. After decrementing n to 2, we proceed to the third group of operations. Here, we start with current equal to 2. Multiplying by 1 gives 2, and since the first_group flag is still false, we subtract this current value from the result, leaving us with 12. With n now equal to 0, we exit the loop. The final output for clumsy 10 is 12. Finally, let's consider a simpler case with clumsy 1. We initialize the variables. N is set to 1, result is 0, and first_group is true. Since n is already 1, we begin with current equal to 1. As this is the first group, we add current to result, updating it to 1. We then decrement n to 0. With no remaining values of n, we exit the loop and return the result. The final output for Clumsy 1 is 1. To analyze the time complexity of our solution for the Clumsy Factorial problem, we start by examining how the input n is processed. The algorithm uses a while loop that reduces n by 1 during each iteration. This means the loop will execute approximately n times. Within each iteration, several operations are performed, including multiplication, division, addition, and subtraction. Each of these operations takes constant time, or O1. Importantly, even though some operations are conditional, their frequency is limited to a maximum of 4 per iteration. As a result, the contribution of operations within a single iteration remains O1. Combining this with the loop running O(n) times, the overall time complexity of the algorithm can be expressed as O(n) times O1, which simplifies to O(n). Now let's consider the space complexity of the solution. The algorithm uses a fixed number of variables, such as result, first underscore group, and current, to keep track of intermediate values. These variables require a constant amount of memory, which means their space usage is O1. Additionally, the algorithm does not rely on any external data structures like arrays, stacks, or lists. All operations are performed directly on the variables, ensuring no additional memory is allocated based on the input size. Because the memory usage is invariant of the size of n, the overall space complexity is constant, or O1. Furthermore, whether we analyze the best, average, or worst-case scenarios, the algorithm's behavior remains consistent, as it always processes all numbers from n down to 1. Therefore, the time complexity remains O(n), and the space complexity remains O1 across all cases. A useful way to appreciate the efficiency of this solution is by comparing it to a brute force approach. In a naive implementation, we might use a stack or a list to store intermediate results while processing each operation. This would increase the space complexity to O(n), as the memory usage would scale with the size of the input. Additionally, the time complexity would also be O(n), as we still need to process all n numbers. However, the optimized approach we've discussed avoids the use of such additional data structures, keeping the space complexity at O1 while maintaining the time complexity at O(n). Mathematically, the loop iterates n times, and each iteration performs a constant amount of work. Multiplying these two factors confirms our final time complexity of O(n). Since the memory usage is constant and does not depend on the size of the input, the space complexity remains O1. When working on the Clumsy Factorial problem, there are a few common mistakes to watch out for. One frequent error is misunderstanding operator precedence. Since the sequence alternates between multiply, divide, add, and subtract, failing to respect the order of operations can lead to incorrect results. For example, division must be performed before addition or subtraction unless you use parentheses to enforce the correct order explicitly. Another mistake involves integer division errors, especially in languages like Python, Java, or C++. Since this problem expects integer division, using floating point division can produce unintended results. Always ensure you're using the appropriate operator for your language, such as // in Python. Off by one errors are another pitfall. Because the factorial decreases step by step, it's easy to miss the base case, such as when n equals 1, or skip the final operation entirely. Testing edge cases like n equals 1 and n equals 2 will help catch these issues. Inefficient computation is another concern. A naive approach that calculates every factorial and evaluates the operations step by step becomes slow for large inputs. Instead, look for patterns or ways to simplify the operations. Lastly, small values of n, for instance, n less than or equal to 4, may not complete a full cycle of operations. These cases often require special handling, so make sure to test them thoroughly. Now, let's focus on insights that are particularly useful during interviews. A key observation is that the sequence of operations repeats every 4 steps. For larger values of n, you can use this repeating pattern to break the problem into manageable chunks of 4 and handle any remaining numbers separately. This approach not only simplifies the logic but also makes the solution significantly more efficient. Speaking of efficiency, recognizing this cyclic nature allows you to optimize the solution and reduce the time complexity from O(n) to O1 for large inputs. This can be achieved by leveraging modular arithmetic to directly compute the results. When discussing your solution with an interviewer, it's important to highlight the trade-offs between a straightforward, naive approach and an optimized solution. While the naive solution might be easier to understand, it's less efficient, especially for larger inputs. Demonstrating your ability to adapt to constraints and find efficient solutions is a valuable skill. Finally, don't forget to address edge cases explicitly. Mentioning scenarios like n equals 1, n equals 2, or n equals 4 shows that you've carefully considered all possible inputs and understand the problem thoroughly. To deepen your understanding of the clumsy factorial problem, it's helpful to explore related problems. For instance, LeetCode 227, Basic Calculator 2, focuses on operator precedence and sequential computation, which is directly relevant here. LeetCode 772, Basic Calculator 3, introduces parentheses and more complex expressions, making it a natural extension of the ideas in this problem. LeetCode 2, Add two numbers, while unrelated to operators, tests your ability to handle sequential computation with constraints, which is a transferable skill. LeetCode 191, Number of 1 bits, emphasizes sequential bitwise operations, another example of applying operations systematically. In terms of alternative approaches, one option is brute force, computing the factorial traditionally and then applying the operations in sequence. This method is simple and clear but becomes inefficient as n grows. A more refined method involves recognizing the repeating pattern in the operation sequence every 4 steps. Leveraging this pattern allows you to compute results directly, especially for large values of n. Another approach is stack-based. Here, you push numbers onto a stack and perform operations sequentially. This aligns with the style of problems that involve evaluating expressions and is often more intuitive, though it may require additional memory. Choosing the right approach depends on the constraints and context of the problem you're solving. Great work! We've explored how to solve the clumsy factorial problem efficiently, using modular patterns and thoughtful arithmetic. Remember the key takeaways about optimizing factorials and applying modular arithmetic. Thanks for joining, and see you in the next problem-solving session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!